Hi, today we look at the electrostatic boundary conditions. Okay, electrostatic boundary conditions. These are the boundary conditions for the electric field. Okay, so what we are considering is a surface charge. Okay, this is a surface charge, this is a surface. The surface charge density is sigma, and there is electric field above and below the surface. Okay, electric field above and below the surface, and how this electric field is changing, how the electric field is changing across the surface. Okay, when we cross the surface, that is what we are going to see here. So the electric field above and below, is there any discontinuity in the electric field? That is what we are going to look at. So for that we consider a Gaussian surface. Okay, we are going to use Gauss's law. So a Gaussian surface is a must that we know. The Gaussian surface that we are considering is a thin pillbox, wafer thin pillbox. So this is the pillbox that we consider. So this is actually a very thin box extending equally above and below the surface. Okay, the thickness of this box is very small. So this epsilon, that is the thickness of the box, that tends to 0. Okay, and it extends equally above and below the surface. Okay, so this is the Gaussian surface that we consider, and here we apply Gauss's law. Gauss's law we know, that is integral surface E dot ds. This is the total flux passing through a closed surface, that is equal to Q enclosed by epsilon 0. Q enclosed is the charge enclosed by the surface by epsilon 0. Okay, so we are considering a closed surface. So that is the surface of this pillbox. Okay, the surface that we consider is the surface of this pillbox, that is a closed surface. So that is equal to charge enclosed by the surface by epsilon 0. We know this surface that we consider, it has a surface charge density sigma. The area of the top and the bottom surface of the pillbox, or the area of this section, that is A. So this is equal to sigma A, the charge enclosed. Okay, this is a surface charge density. So the area of this section is A. So the charge enclosed is sigma into A over epsilon 0. Now what is this integral E dot ds, the flux? For that we have to consider the top surface, bottom surface, and the side surface. Okay, we have to consider the top surface, bottom surface, and the sides. Okay, the sides of the box. So that is what we have written here, integrals the top surface E dot ds, bottom surface E dot ds, the sides, and this part is taken as 0. From the sides it is taken as 0 because why? Epsilon tends to 0, the thickness tends to 0. So this is the E dot ds for the top surface, that is integral E cos theta ds, and this E cos theta ds is a vector normal to this surface. Okay, ds is the small area vector that is normal to the surface. So E cos theta E is the electric field. It can be in any direction. E cos theta is the component of the electric field normal to the surface. Okay. ds normal to the surface. E, that can be in any direction. Theta is the angle between the electric field and ds. And E cos theta is the component of the electric field normal to the surface. Okay. So that is written here, E perpendicular, that is E normal. And here for the bottom surface, we are calculating, for the bottom surface we are calculating E dot ds. And for the bottom surface, see, for the bottom surface ds, that will be downwards, that will be in the downward direction. Okay, that is just opposite to the ds on the top surface. So for the bottom surface, ds will be pointing downwards. Okay, so here we have this integral E cos theta ds, and this E cos theta is E perpendicular below, and here we have taken negative. Okay, negative sign because the ds is pointing downwards. So I am writing E normal or E perpendicular above. A is the total area of the top surface, and here minus E perpendicular or E normal below. A is the area of the bottom surface. Okay, these two areas are same. So we get this expression for the total flux passing through the surface. So E perpendicular above, A minus E perpendicular below. A, this is the flux, that is equal to sigma A over epsilon 0. So this A will get cancelled. So you have E perpendicular above minus E perpendicular below, that is equal to sigma by epsilon 0. Okay. So this is the first boundary condition that we get. E perpendicular above is the component of electric field perpendicular to the surface immediately above, and E perpendicular below, component of the electric field perpendicular to the surface just below. So we see this is not equal to 0. E perpendicular above minus E perpendicular below, that is not equal to 0. If it is 0, these two will be same. E perpendicular above will be equal to E perpendicular below. Okay. So the normal component of the electric field is not continuous. If this was 0, right hand side was 0, the electric field would have been continuous. But since it is not equal to 0, this is discontinuous. So the normal component of the electric field is discontinuous. It is discontinuous by an amount, sigma by epsilon 0. Okay. Now, so that is all about the normal component. Then what about the tangential component? Okay. So here, for this box, I am considering a rectangular path. On one side of the box, I am considering a rectangular path. A, B, C, D. Okay, so half of the path is above the surface and half of the path is just below the surface. Okay, I think it is clear to you. A, B, C, D. That is a rectangular path. This half of the path is above, half of the path below the surface. Okay, so we have this A, B, C, D. So line integral, the thickness of this path, that is epsilon, that tends to 0. We are considering a very thin rectangular loop, A, B, C, D, A. Now we know the line integral of the electric field around a closed loop is 0. Okay, line integral of the electric field around a closed loop is 0. That's why we have this del cross E equal to 0. So line integral of the electric field around a closed loop is 0, E dot dl is 0, that is written here. And we are considering this loop. We start from A, we move to B, then from B to C, then from C to D, then get back to A, from D to A. So that is written here. A to B E dot dl, B to C E dot dl, C to D E dot dl, D to A E dot dl. Okay. So the line integral of the electric field around a closed loop. Now as epsilon tends to 0, epsilon is the thickness of the loop. As it tends to 0, this one integral A to B E dot dl, that will be equal to integral C to D E dot dl, that is equal to 0. A to B, C to D, epsilon tends to 0, that integral will be equal to 0. And for B to C E dot dl, what is B to C? From this point to this. Okay, D to A, that is in opposite direction. Okay, that we have to consider B to C, then D to A. D to A is opposite to B to C. So integral B to A E dot dl, that is equal to as we did integral B to C E dot dl equal to integral B to C. This we are writing E cos theta dl. dl is along this B to C. Okay, dl is along B to C. So E dot dl, E cos theta dl is the electric field that may be in any direction. E cos theta is a component of the electric field along dl, along the path. Okay, so that is the tangential component or the parallel component, the component of the electric field parallel to the surface. So E parallel above into L. Okay, integral dl we take, that is total length L from B to C. Then from D to A in the opposite direction, E dot dl, that is equal to minus. Here we are taking minus because this is opposite to the dl that we consider here. The dl that we consider here, it's opposite to that. So minus integral D to A E cos theta dl, that is minus E parallel below L. Okay, E cos theta is the parallel component or the tangential component below, because A to D is the path below the surface. So this is equal to E parallel above L minus E parallel below L. Okay, the total line integral of the electric field along the closed path. So that is equal to 0. So E parallel above is equal to E parallel below. So the parallel components, they are equal. So there it is continuous. Okay, so the parallel or the tangential component of the electric field is continuous. The normal component of the electric field is discontinuous. So we are combining the equation 1 and 2. Okay, we are combining equation 1 and 2. We can write it in this form: E above minus E below. Okay, so this is just the electric field above, and this is the electric field below. Okay, that is equal to sigma by epsilon 0 n, where n is a unit vector perpendicular to the surface from below to above. Okay, so n is a unit vector from below to above. N is unit vector pointing from below to above. Okay, so that is written here. So E above minus E below, that is sigma by epsilon 0 n. Now the boundary conditions on potential. So far we saw the boundary conditions for the electric field. Okay, when the two conditions 1 and 2 that we combine here like this. So when we are taking the normal component, we will have E perpendicular above, E perpendicular minus E perpendicular below equal to sigma by epsilon 0. When we are taking the tangential or the parallel component, since this gives only the normal component. The right hand side gives only the normal component. This will be equal to 0. So E tangential above minus E tangential below, that will be equal to 0. Okay, so that's about the electrostatic boundary conditions for the electric field. Now we see the boundary conditions on the potential. So again the surface, this is the surface charge density. A is a point just below the surface. Okay, A is a point just below the surface. B is a point just above the surface. Okay, so you consider surface. A is a point above, sorry, A is a point below, B is a point above the surface. Now we take VB minus VA. VB minus VA is the potential difference between the 2 points. That is equal to minus integral A to B U dot dl. This is a definition for the potential difference. VB minus VA equal to minus integral A to B U dot dl. Now if the path shrinks, if A and B are very close together, okay, A and B are very close together, and if the path shrinks, path length shrinks to 0, VB minus V, this right hand side will be equal to 0, because the path itself is too small. So this will be, the line integral will be equal to 0. So VB minus VA equal to 0. So VB equal to VA. So VB is the potential above, VA is the potential below. These two are equal. VB equal to VA. So V above is equal to V below. So we say the potential is continuous across the boundary. The potential is continuous across the boundary. Okay. So the potential is same below and above. Now E above minus E below, that we just saw, that is equal to sigma V epsilon 0 n. And we know there is a relation connecting electric field and potential. What is it? E equal to minus del V. Okay, E equal to minus del V. Electric field is negative gradient of the potential. So we are writing here minus del V above, here minus del V below. Okay. So we take this negative sign here on the right hand side. So del V above minus del V below, that is equal to minus sigma by epsilon 0 n. Okay, here n is unit vector. We know the direction of unit vector. Now del V above dot n, we are taking the dot product. We know del V, it's a vector, so I'm taking dot product. So del V above dot n minus del V below dot n, that is equal to minus sigma epsilon 0 n dot n. N dot n is 1. Okay, so del V gradient of the potential above dot n minus gradient of the potential below dot n, that is equal to minus sigma by epsilon 0, because n dot n, dot product of a vector with itself, is 1. Now we are writing this del V dot n. Okay, del V dot n, that is written as dou V by dou n. That denotes the normal derivative of V. Okay, this is called the normal derivative of V, the rate of change of V, the rate of change of V in the direction perpendicular to the surface. The normal, the normal derivative of V. So del V dot n, that is called, that is dou V by dou n, that is the normal derivative of the potential. So this is dou V above by dou n minus dou V below by dou n, that is equal to sigma minus sigma by epsilon 0. That is the normal derivative of the potential that is, discontinuous. Okay, potential is continuous. The normal derivative of the potential is discontinuous, that is equal to minus sigma by epsilon 0. So this is what happens for the electric field and the potential across a surface charge, across the boundary of a surface charge. The electric field, the normal component is discontinuous, the tangential component is continuous, and the potential is continuous across the boundary.